Let's recap what we saw in a previous video about atoms. We saw the nucleus. It contains protons, positively charged particles, and neutrons, neutral particles. Orbiting the nucleus are the electrons, negatively charged particles, creating a cloud around it. These tiny particles come together to form molecules, like the water molecule. This occurs because an electron from one atom, in this instance, the hydrogen atom, gets trapped in an outer energy level of another atom, which here is the oxygen atom. This electron capture forces the hydrogen atom to stay close and follow the oxygen atom, and thus to create the water molecule. Furthermore, water molecules cluster together due to the formation of hydrogen bonds, which occur because the opposite charge of hydrogen and oxygen atoms naturally attract each other. A fascinating aspect of the microscopic world is that electrons, unlike most matter we see around us, don't exist in a way we typically understand. This is because they can behave both as waves and as particles. We can't pinpoint their exact location, but can only determine the probability of where they might be. So far, electrons cannot be described with words or images, as they are essentially clouds of possible locations and nothing more. Within the nucleus of an atom are protons and neutrons. Unlike electrons, which are elementary particles and not made up of other particles, protons and neutrons are composed of even smaller particles called quarks. Quarks come in different types, and protons and neutrons are each made of 3 quarks held together by a strong force. Quarks have been experimentally proven to exist since 1968 and are considered elementary particles because they cannot be broken down into smaller parts. In nature, there are 12 elementary particles, 6 quarks and 6 leptons. The 6 types of quarks are up, down, charm, strange, top, and bottom. Each type of quark has unique properties, including electric charge and mass. The 6 leptons include the electron, muon tau, electron neutrino, muon neutrino, and tau neutrino, each possessing its intrinsic properties as well. Inside each proton and neutron, the quarks reside, forming the particles in the nucleus of atoms. The strong force that holds them together can be imagined as a spring that binds them together. Since the longer the distance between them, the attraction force increases dramatically. This is why we cannot detect them separately in nature, only in groups, the protons and neutrons. So far, we don't have the equipment to separate them. The strong force that binds quarks together is carried by particles known as gluons. Gluons are responsible for keeping the quarks in place. You can think of it as quarks passing gluons among themselves, which is how they remain firmly connected. This is our current understanding of how particles stick together, although it may not explain every aspect of this phenomenon. The complete understanding of particle cohesion eludes us. The concept of force carriers, as revealed through scientific experiments, remains our most plausible explanation. These carriers are vital in bonding atoms and ensuring the stability of our world. Quarks are the fundamental building blocks of all matter. Understanding these amazing particles helps us appreciate the deeper structure of the tiny components that make up everything around us. To complete the picture, let's revisit the atom. At a larger level, the protons and neutrons in the nucleus enjoy a strong bond thanks to the powerful, strong nuclear force. It is the same force that ties the quarks together through gluons. Although this force is tremendously powerful, it operates only over very tiny distances, about the size of the nucleus itself. This is why we don't experience its effects on larger scales, and why we can't feel it acting on our bodies. Try imagining the size of the nucleus. Knowing that the average size is 10 to the power of minus 14 meters, while an average human body has a height of 1.74 meters. It has absolutely no effect at a larger scale on the human body. It does not even affect the electrons orbiting the nucleus, which do so at a distance of 10 to the power of minus 10 meters, a distance of 10 to the power of minus 4 meters apart.